So the next speaker is Gabrielle Benedetti from Leipzig. And as you can see, I don't have to tell you what is the talk, what's the title of his talk, right?
Okay, thank you very much for the introduction. And it's nice to be here. Thanks for the invitation to the organizer. So today I'm going to talk about systolic inequalities in contact and odd symplectic geometry. This is a joint work with Jiangsu Kang, who's here in the audience. And so classically, systolic inequalities were originally formulated in the context of Riemannian geometry. And these inequalities try to answer the following question. So given a Riemannian manifold, is it possible to find a closed geodesic whose length is controlled, the length of this geodesic is controlled in terms of the volume of the Riemannian manifold? And then recently, Alvarez-Paiva and Balashev reformulated this inequality in the context of contact manifolds and gave some strong indication that a local version of this inequality should hold for contact manifolds. And in this talk, we are going to speak about, a little about this local inequality, and we are going to see some applications to magnetic flows on surfaces. And in the very last part, we try to widen the horizon a bit further and try to look at a version of this inequality for odd symplectic manifolds. Okay, so let's start with the contact geometry setting. So one, this is contact geometry. So I considered sigma here. This is a manifold of dimension 2n minus 1. This is closed and oriented manifold. And then on it, I consider a co-oriented contact structure, co-oriented contact structure. On sigma. And then, as was already pointed out, so once I have a contact structure, I can consider the set of contact forms supporting this contact structure. These are the contact forms supporting psi. Okay, so here I have a form alpha. And then I know that it's the kernel of alpha x psi. And then associated to alpha, we have the Reb vector field, R alpha. And we have the corresponding flow, which I denote by phi of alpha. Okay, so then this systolic inequality in this case boils down to try to answer the following question. So is there some constant, C of psi, bigger than 0? So this constant should depend only on the contact structure, such that for all contact forms alpha supporting psi, we can find gamma. This is a periodic orbit of the Reb flow. Also, by this symbol here, P of alpha, these are simply the periodic orbits of phi alpha, such that the period of this orbit, gamma, is bounded by this constant, C of psi, times the volume of alpha. And then here I have to renormalize the volume so that they scale accordingly when I multiply alpha by a constant. So I have to put here the nth root of the volume. Okay? Whereas the volume here, so I just recall the definition, the volume of alpha is just the integral over sigma of alpha wedge d alpha to the n minus 1. Okay? And then, so as it, we can slightly rephrase this question in a way, so here there is question mark. So you can slightly rephrase the question in a way that's convenient for us later. So the question now becomes, is the systolic ratio, which is a function, rho, defined on the space of contact forms, into 0 plus infinity, which is defined sending alpha to the minimal period of a periodic orbit, a closed periodic orbit of alpha, to the n divided by the volume of alpha. So is then this quantity bounded from above? Okay, so if this quantity is bounded from above, then there exists these constants, and then also the other way around. So this is really a question about this function. So we want to know if this function here is bounded from above or not. And then the answer is that it's no in general. So the answer is no. The first counterexample was given when sigma is the trisphere and psi is the tight contact structure. And this was given by Abbondandolo, Brahman, Riniewicz, and Salmão. Okay, so and probably this example is far more general than it is at the moment. So they can show it basically in this case. So this means, so this case here is simply the case where our contact structure comes from a star-shaped domain in R4. And basically they're saying that if I can choose, for example, star-shaped domains with fixed volume, 1, but the shortest characteristic on the boundary of this domain is arbitrarily long. So this is like rephrasing the result. Okay, so this means that globally there is no, this bound here is not available. So what we are trying to do today is like to look at a local question. So if I fix now a form here, what happens if I perturb this form a little? What happens to this systolic ratio? And then here for this local study, this is meaningful when we start with a contact form, which is a critical point of this rho. Okay, and so the first result in this local study is the characterization of forms which are critical points of this systolic ratio. And then we have the following proposition or theorem. So this is a critical point of the systolic ratio if and only if alpha naught is a Zoll form. And this is due to Alvarez-Paiva and Balashev. What does it mean that the form is Zoll? So in the literature, there are several way to call such forms. This is simply a Butby-Wang form or a regular form. So this means simply that the rep flow of alpha naught yields a free S1 action on sigma. Okay? And then for the purpose of this talk, so we can always renormalize alpha 0 so that this action has period 1. And for the purpose of this talk, when I say S1, I always mean R quotiented by Z. Okay, so length 1. So let's have a look at this case a bit more in detail. So what happens here? So we have then our manifold sigma, and then I can consider the quotient of sigma by this action. And then I call this manifold here M. And this is then the projection P. This manifold here is a closed smooth manifold of dimension 2n minus 2. And now if I consider here above the differential of the Zoll form, this descends to a symplectic form on M. So d alpha naught is P star of omega naught, where omega naught now is a 2 form on M, which is symplectic. Okay? And then, so now P becomes really a principal S1 bundle. And alpha naught becomes a connection form for this bundle. Connection form for P. And this in particular means that if I take now the RAM class of omega 0, this is an element in H2 the RAM of M. This here is minus the Euler class of P. So it's like a topological, topologically given just by the bundle. Yeah.
So normally there are no critical points.
Yes. Yeah. So.
Okay. And if you have a contact form whose wave flow is quasi-free, not free, so that's not a.
Yeah. That.
Is enormous, that won't be a critical point.
There won't be a critical point, but maybe in this case one can a bit change this definition of T-mean. Maybe one can look for T-mean in some free homotopy class, maybe different from the standard one. So yeah, this is actually an interesting question, how much what I say today generalize to this quasi-regular stuff. Yeah. Okay, so this means the Euler class, and then this means in particular that, I write it here, that if I take now the volume of M with respect to this omega 0, this here is a positive integer, and I denote it by K. Okay, this will play a role later. Okay, so these are now, so I've given the definition of Zoll forms, I've seen some properties, and now, so we have seen that these are exactly the critical point of rho, and now there is a conjecture saying what kind of critical points they are. Okay, so this is the conjecture. So we fix now some integer m bigger or equal than 2. And then the conjecture says that if alpha naught in form psi is Zoll, then there exists U, a neighborhood of alpha naught in CM neighborhood. So here this is where this integer here plays a role. This is CM neighborhood of alpha naught in the space of contact forms, such that for all alpha in U, then the systolic ratio of alpha is less or equal than the systolic ratio of alpha naught. And we have the equality here if and only if alpha is Zoll. Okay, so this basically says that the space of Zoll contact forms is a strict local maximizer for the systolic ratio. Okay? And so actually it's expected this should be true with m equal to 2, but so far the methods cannot reach this level of generality. And then Alvarez-Paiva and Balashev gave some kind of prove some kind of weaker statement about this conjecture. And now we are going to see, like, give an idea why the conjecture should be true, or what is the idea behind the conjecture. So this is like baby case. So if I now take f to be a function from m to 0 plus infinity, so m is my quotient manifold, then I can just consider alpha to be f times alpha naught. And in this case, the volume of alpha is simply the integral over m of f to the n times omega naught to the n minus 1. And moreover, so now if q is a point in M, then q is a critical point of F if and only if the fiber over q by this bundle P, this is a Reb orbit. Okay, and actually in this case here, the period of the orbit is just the value of the function at q. So we have done a correspondence between critical points and periodic orbits such that then the period corresponds also to the critical value of f. Then what does it mean? This means that if I now take the systolic ratio of alpha, so above I have the minimal period, so this will be certainly smaller than the minimum of f to the n. And below I have the volume, so this is the integral over m of f to the n times omega 0 to the n minus 1. And here I can just use here the minimum of f, here below. And here I get times m omega 0 to the n minus 1. So this is just 1 over k, which is also rho of alpha naught. Okay? So we see that in this case the systolic inequality holds. And then actually here we have the equality if and only if f is constant. Which means if and only if, yes, if and only if f is constant, if and only if alpha is zone. Okay, so this is like the idea for this special class of contact forms, and then what Alvarez, Paiva, and Balazs did in their trying to prove the conjecture is to approximate an arbitrary contact form with such contact forms to higher and higher order. Okay, good, but okay, so this is the idea why the conjecture is expected to be true, and then. So recently, the conjecture was also established in a kind of its full power, almost, by Abbondandolo, Brahman, Liniewicz, and Salomao, when sigma is the trisphere. So the conjecture holds if sigma is the trisphere. And the topology is the C3 topology. So here it's almost like what one expects. Okay, and then with Jiangsu, we built on this result, and then we proved that the conjecture actually holds for all three manifolds. If dimension of sigma is equal to 3, and then m is equal to 3. Okay. And now what I want to do next is like to give some ideas of the proof. So I will not be able to give all the details, but I will present the two main ingredients that we use during the proof. Is there any question? we have now ingredients of the proof. Ingredients of the proof. So remember that now, so we are considering now a contact form alpha, which is C3 close to our Zoll contact form alpha naught. And then here for alpha naught, I have this bundle. And now I'm considering gamma min of alpha. This is the minimal periodic orbit for phi alpha. Okay, so I want to estimate the period of this periodic orbit. And then the first ingredient of the proof is the construction of a global surface of section. Construction of a compact global surface of section, which I denote by I from S into sigma. So here S is a compact surface, E is a map into sigma, and then basically this map has these properties that Dan also listed before. I'm going to repeat them here. So the first hypothesis is that the Rep flow is transverse to the interior of S. The second one is that the boundary of S is the union of periodic orbits. The union of orbits in P of alpha. And the last condition is that every flow line of phi alpha hits I of S in the future and in the past. Future and in the past. Okay? And then in this case, we can give some, so we have a really concrete example for this S. So what is this S? So the topology of the S is the topology of M. So genus of S is equal to the genus of M. And the boundary of S is connected. And when I restrict I to the boundary of S, I just get this orbit, the minimal orbit, iterated k times, where k was this integer I defined before. Okay, so if, for example, here is M, then S is just something like this. So this here is the boundary. And so now I also explained by Dan before. So once we have a surface of section, we can reduce our Rep flow to a kind of Hamiltonian diffeo of the surface. So if I take now some Q here, I know that by the first property, I will leave the surface in transverse direction. Then I go somewhere. I come back. And then I hit the surface here again at some point. And this point here I call phi of Q. And this is just obtained by flowing with alpha for some time tau of Q from point Q. Okay, so what I get here is then a return time tau from S into 0 plus infinity, and a return map S from S. And then since we know that alpha is C3 close to alpha naught, I get that tau is C1 close to the function 1, and phi is C1 close to the identity of S. Also here is where we use crucially that we have the C3 topology, because here we want to get exactly the C1 topology. Also, if one can get this C1 topology here with something less here, then it's better. But here, we want to arrive here to have the C1 topology. Okay, so this is phi and tau. And then we have, as I said before, this phi will be a Hamiltonian map. So we have some additional piece of data here on S, namely the one form lambda, which is the pullback of alpha. And then this d lambda is a symplectic form on the interior of S. And on the color neighborhood of the boundary, it has like a standard form. This is minus r dr wedge d theta. Okay, this is on a neighborhood of the boundary, which is diffeomorphic to 0, 1 times S1. Okay, where r equal to 0 is just the boundary. And yeah, so we see that here at the boundary, the form is not symplectic anymore because this term here vanishes of order 0. Of order 1, sorry, vanishes of order 1. No, so it's like as a 0 of order 1. And, but nevertheless, we have this compatibility condition, so phi star of lambda minus lambda, this is d of tau. And then this is the key to bring our problem to a problem on maps on S, which satisfy this condition. And I will not say exactly what this kind of dictionary is, but there is such a dictionary bringing this information on rep flows, on information on maps, satisfying such conditions, and back. Okay, so this is our map, phi, which then preserves d lambda. And then for the second ingredient in the proof, we need to see that this phi can be generated by a special Hamiltonian. Okay, so second ingredient, ingredient B. This is, there exists some quasi-autonomous Hamiltonian, HT from S into R, with Hamiltonian flow with flow phi of t, such that the time one map of this flow is exactly our phi, such that phi is equal to phi of 1. Okay, so this is the second ingredient, and then when we have this, then basically the proof is very similar to the baby case, so this is the second important thing. And here, by quasi-autonomous, I just mean that I want the existence of some point Q minus on S, such that for all time t between 0 and 1, then the minimum of the Hamiltonian HT on S is always equal to HT of Q minus. Now, so this Q minus is for every T a minimizer of the Hamiltonian. Okay, so this is like the key property. And then classically, in order to get such Hamiltonians, one uses this Weinstein neighborhood theorem for symplectic manifolds. No, so how do we get this? So how? This is a Weinstein neighborhood for the manifold S lambda. So what I mean by this, so I have here S times S, with symplectic form lambda plus minus lambda. Okay, so I draw a very simple picture. So this is S times S, so S times S. And then here we have the diagonal of S. And then this is an exact Lagrangian here inside this, symplectic manifold. And then on this other side, I can consider the cotangent bundle of S with a standard symplectic form. Okay, so on this side, then we have here the zero section, and this is like the cotangent bundle. Okay, then the zero section is also an exact Lagrangian, and then this Weinstein neighborhood theorem tells me that I can find a neighborhood of the diagonal here. So something like this. Something like this. And here, a neighborhood of the zero section, such that this neighborhood is isomorphic with an exact diffeomorphism to this neighborhood. So this would be the standard Weinstein neighborhood theorem. But in this case, our form here is singular at the boundary. So the fact is that on this side here, we don't get quite a neighborhood. I denote it by n tilde. This will be a neighborhood which is pinched at the boundary. Okay, so there is some kind of pinching. So here I don't get a real neighborhood at the boundary. But this is still enough for our purposes, because now if I have some map phi here on S, I can see inside this neighborhood, if phi is C1 small, the graph of phi, which is a Lagrangian graph. And then here I will see some other graph. And then this graph would be the differential of a function, since this is an exact map. And then this is the function W phi from S to R. This is called the generating function. And now we can get our flow of phi t generated by quasi-autonomous Hamiltonian if we are able to go back to invert this arrow when here we take, instead of W phi, we take t times W phi. So we scale W phi to 0, and then we want to be able to go back here to get some phi of t. No? And then the question is that if we can do this, and in order to do this, we have to know something about this neighborhood n tilde of S. And so this is the last observation that completes the proof for this ingredient, at least. And then here the key is that now this set of W phi, such that phi is C1 small, can be characterized as a set of all W, such that W is C2 small, D of W vanishes at the boundary, and 1 over R times dW is C1 small on this neighborhood of the boundary. So we can give such a characterization of all the possible generating functions that can arise. And then now the observation is just that this set here is star-shaped around the zero section, the zero function, star-shaped around zero function. Okay, so that then we can do this squeezing of W to 0. Okay, so this is like the second ingredient of the proof. Is there any question about this part of the talk? Yep. Yeah, so we first construct the surface of section for alpha naught, for the Zoll contact form, and then we perturb the surface of section that we get in this case to a surface of section of phi of alpha. No? So in the case of alpha naught, then one just observe that S, the interior of S, is diffeomorphic to M minus a point. No? So it's like here I'm taking M and I'm removing a point. And now the fact that we have a surface of section for the flow of alpha naught simply says that this surface of section is a section for the bundle, like in the bundle sense. No? So then I can, from this, I can always construct a section restricted to this space, because this is now an open two-dimensional manifold. So I can always construct here P section. And then the fact now that I know that the Euler number is K tells me that now around the point Q here, I can take a small neighborhood, and I will have here polar coordinates, r and theta. And then my section here will look like something like r times e to the 2 pi theta. And then here, this is minus k times theta, something like that. So, and here, this is like a trivialization. This is in d2 times s1. This is just a trivialization of the bundle over this thing. And then now this gives me then the section for alpha naught, and then for alpha 1 just perturbs this. Yep.
So this minus is very important. Minus k times
Yes. This is this k is different from 0. Yes, yeah, exactly. Yeah. Okay, then I go to the application. Okay, so this is the second part of the talk. It's an application.
Sorry,
Yeah.
I didn't quite follow with k being non-zero. You're saying are you worried that near the boundary a flow line might not turn? What could go wrong if k is 0?
Yeah, no, the fact is that if k is 0, then the boundary is, so it's not covering a periodic orbit, so to say. Yeah. So this is at least the first problem that I see. Then maybe it has also some other problems. So in general, you cannot have so the fact is that if you have a Zoll contact form, then the bundle must be automatically non-trivial. So you never see the case k equal to 0. So it's not possible. So yeah, one can.
So, but what were you talking about with the speed?
If I could have a minus k there, tells you that a fiber here, a fiber 2, has linking number, has intersection number plus k.
Yeah, this is also, yeah. Yeah, but, okay, so application. So these are the application on curves with prescribed geodesic curvature on surfaces. Okay, so also known as magnetic geodesics, or maybe with also other names. So what I have here now, it's M2. This is a closed oriented surface. And then I fix on this M also a Riemannian metric, G. And now, for every f, which is a function from M to R, which I interpret as prescribing this geodesic curvature, I will define a set of curves, like having this f as the geodesic curvature. Okay, but prior to doing that, I just define this quantity. This is just the average of f. So I take f, and I integrate it over the manifold against this area form. And I just divide by the area A. This is the total area. Okay? And then for what I'm telling you now, then we assume that this number here is non-negative. Otherwise, we have to use a bit more complicated notation, but then just stick with this case. So up to changing the sign of f, we can always have that this is the case. And then I can define the set of curves I'm interested in. So C, this is a curve from an interval into M, which is an immersion. This is called an F geodesic. If for all time in the interval, the geodesic curvature Kc at time t is equal to f at the point C of t. Now this is here just the geodesic curvature. Geodesic curvature. So as I said before, this is just a way to prescribe, this f is just a way to prescribe the geodesic curvature at every point. Okay? And now we can ask now if to describe the closed curves satisfying this property. And we will see that then these closed curves, if I restrict the set, so my setting sufficiently enough, then they will be critical points of some functional. Okay, so now, let curly E plus, this is the set of curves C from S1 into M, such that C is just the boundary of a disk. C is just the boundary of a disk, which I call capital C. C is a disk. And then what I require about this disk is that if I take now the lift of the disk to the universal cover of M, this is positively embedded. Okay, so I'm just looking now, I will look for curves satisfying this equation into a subclass of curves. So this subclass is defined independent of F. These are all the curves, C, which are boundary of some disk, capital C. And this disk has the property that when I lift it to the universal cover, this is a positively embedded disk. Okay, so for what we say, that it's enough to look for solutions inside this space. And now on this space, I can define a variational principle, LF. I just take a curve C, and I consider now the length of C with respect to the metric G, and I subtract the area, the F area of the disk. Okay, and then this is a variational principle for F geodesics. Now, meaning that the critical points will be F geodesics. And so we can also define the critical value, or something that I would like to be a critical value, L mean of F. This is defined as the infimum over all C in this space E plus, which are also F geodesics, of the quantity LF of C. Okay, so in general, so this is not a critical value because this infimum maybe is not a minimum. But we will see that in the case we consider, then this is actually a critical value. Okay, so we have now defined the critical value that plays a bit the role of our minimal period in this setting. And now I want to give the definition of Zoll function f and of the systolic inequality in this setting. Okay, so definition. So we say that f is Zoll if all f geodesics are closed and lie in E plus. So if all lie in E plus, basically. Okay. And then the second definition is that we say that f satisfies the magnetic systolic inequality. Magnetic systolic inequality if the following two things are true. So first thing is that this quantity, delta f, which is defined as f squared plus 2 pi k of m divided by a, is positive. Okay, so this is the average of f, this is the other characteristic of m, and this is the total area. So we want, first of all, that this quantity is positive. And then when we have this, we want that the minimal length of f is less or equal than 2 pi divided by the average of f plus the square root of delta f. Okay, with equality if and only if f is Zoll. Okay, so we say that f satisfies the magnetic systolic inequality if this is true, so that delta f is positive, and then we have this bound for the minimal length, f length. Okay, and then now I'm going to state a theorem that says that in some cases f satisfies this magnetic systolic inequality. Yep. Yeah, so very, very good question. This exists for every surface because you can just take the homogeneous metric on the surface and then f equal to 1. Or maybe you have to rescale it a bit, not so, f constant anyway. But how rich is this space is still like, we don't know basically how many are these Zoll guys. But a nice thing in this setting is that this exists also for surfaces different from Z2. No? While we know that Zoll geodesic flows, they exist only for S2. Okay, so here's the theorem. So f satisfies the magnetic systolic inequality if one of the two holds. First case, f is C3 close to f null, f naught, Zoll. So if f is C3 close to a Zoll function, then satisfies this condition, or f is positive function, and its average, f, is very big, and we can also a bit quantify how big is this average. This should be bigger than the exponential of some constant, C of g, times f bar in square brackets. And now I explain what is this f bar. So where this is just a constant depending on the metric. And this f bar is just the renormalization of f through the average. So I take just F divided by the average. Sorry, average. And then this quantity here is just a quantity defined as 1 plus the C3 norm of F bar divided by the minimum of F bar. Okay, so it's not very important what this F bar is. So the message here is that this must be bigger than some quantity which depends only on the renormalized function F bar. And then we can be a bit more, a bit preciser, a bit more precise. What is it? By saying this. So in these two cases, then we can get this magnetic systolic inequality. And then just a comment. So this second case here, so this inequality here holds, for example, if F is some S times F1, where S is some very, very big constant. No? So because if I rescale some given function, this will grow, but this will stay the same. So this also incorporates all the possible positive functions, F1, if I rescale them a lot. Okay? And here, basically, the idea of the proof is just to observe that if I now take C dot, these are flow lines of a red flow on the unit tangent bundle of M. And then we can use the result from before. But here there's a small caveat. So here, this is true if M is different from the torus. Okay? So if M is different from the torus, then we have this description. If M is the torus, then we had to do something else. And this was the motivation, actually, to consider this more general class of systems, those coming from odd symplectic geometry. Okay? Is there any question? How much time do I have?
10 minutes.
10 minutes? Okay. Good. So let's go then to the third part. This odd symplectic geometry. Okay, so for this, I start always with a manifold of dimension 2n minus 1. This is closed and oriented. And now on this manifold here, I fix capital C. This is a de Rham class in degree 2. Okay, and then given this class, I can consider all the possible forms having this class here. So these are all, where is it? These are closed 2 forms on sigma with class C. Okay, and then if I now fix an element inside this set, I can just describe an arbitrary element of the set as omega star plus the differential of a 1 form. Now this is a differential of a 1 form. Okay, and then the first step to try to generalize this systolic inequality is to give a definition of volume in this setting. And this is the first step. So before, the volume was a function of the space of contact forms, and now the volume will be a function on the space FC. Okay, so how is the volume defined? So the volume now is a function from Fc into R. And then I define the volume by requiring that the volume at this reference form omega star is 0. and then by specifying the differential of this function. And I say that this differential is equal to small volume here, where this small volume is one form on the space Fc. Also, it's one form on the space of closed two forms. How is this volume defined? So I have to take the volume at some point omega, and then I have to give him a tangent direction in this space. But we saw that this space is just basically a space of one forms, no? Because omega star is fixed. So this beta here is just a one form. Okay, and then one can give this very natural definition. One just take beta and integrate it against omega to the n minus 1, okay, in sigma. This gives you a number, and then this is the value of our volume form. Okay, and then this function here, big vol, is just the differential of this small vol. Okay, so for example, when n is equal to 2, one gets that the volume of omega is just the integral of alpha wedge omega star plus 1/2 integral sigma alpha wedge d alpha. Okay, so this is for the case in which the manifold is 3-dimensional, so when n is equal to 2. Okay, in higher dimension, and one gets more complicated expression. Okay, so this is a candidate for the volume. Then we now want to give a definition that generalizes contact forms. These are the odd symplectic forms. Forms with class C. So an element in here, omega, is just an element in Fc, such that the distribution kernel of omega over sigma, this is one-dimensional. Okay, so it's like maximally non-degenerate, and therefore I can consider the curves which are tangent to this distribution. These are the characteristics. So these are curves gamma from S1 into sigma, such that gamma dot belongs to the kernel of omega. Okay, so in this setting, we look for closed curves which are tangent to the distribution. Okay, and we want to give a variational principle for this kind of curves. In order to do that, we do this in a very specific setting. So the setting where we have a Zoll odd symplectic form, which is the next ingredient. This is a Zoll forms with class C. So if I have here omega, what is this? This is just an odd symplectic form such that there exists some bundle P from sigma to M, such that for all points in the base manifold, the fiber over Q is a closed characteristic of omega. Okay, so this is the definition. So basically, we want that we have this foliation by closed characteristics, and they form like a smooth bundle. Okay, so now let's fix some Zoll form. Let's derive some conclusion. Sorry? Yeah, the contact is equal to 0, exactly. Yeah. Okay, so now I fix omega naught. This is a Zoll contact form. And then I erase this, but I choose as this reference form omega star any form which comes from downstairs. This is just some 2 form on M. And then I define E and C. These are two classes in the round cohomology of the base. E is just minus the Euler class of P, while C is the cohomology class of this omega, small omega star. And these are both in H2, the RAM of M. And once I have this E and C, I can cook up a polynomial. Define P, polynomial, from R into R, defined by this property. P of 0 is 0. And then I define what is the differential of P, so the derivative of P respect to X. This is the integral over M of C plus X times E to the n minus 1. Okay, so here for every X, a real number, I have this class in the two-dimensional cohomology, and then just integrate it. It's n minus 1 power. And this gives me this polynomial. Okay, and in some sense, this gives me this relation, will give me this relation between volume and action. So the last thing to do is then to define the action. Okay, let's define the action. So now if I take a not symplectic form C, which is C too close to my Zoll form omega 0, I can define the action A of omega. This will be defined on a space of loops, lambda p into R, where lambda p are just the loops which are C0 close to some fiber of Q. Now, so we are going here to look at neighborhood of the fibers. Now, so here I have my gamma, and here I have my P inverse of Q. These are C0 small, and therefore we can also find here a cylinder, big gamma, between these two orbits. And now how is A of gamma defined? This is the integral over S1 of P inverse of Q star of alpha plus the integral 0, 1 times S1 of gamma star of omega. And this is also a variational principle for these closed characteristics. And then, as before, I can define the minimal action of omega as the infimum among the gammas in lambda p intersection with key of omega of A of omega gamma. Okay, and then what we can get in this context is a relation between this action and the volume when omega is a Zoll form. So this is Kang. Now, if omega is a Zoll it's a Zoll odd symplectic form, which is close to omega 0, then we have the following relation. The polynomial P, which I defined there at A min of omega, this is equal to the volume of omega. Okay, so this is kind of the equality case in the systolic inequality. And then I just finish by stating what is then the conjecture in this case. Yeah, so in this case, then the conjecture is if omega 0 is a Zoll odd symplectic form, then there exists U is a Cm minus 1 neighborhood of omega 0 inside the space of odd symplectic form, such that for all omega in this neighborhood, So, yep. Then PA mean of omega is less or equal than the volume of omega. And then the equality holds if and only if omega is Zoll. Okay, so this is the version of the conjecture, and then basically the conjecture is established in some cases. So the first case is when omega is quasi-autonomous. I cannot say precisely what this means, so it's kind of generalization of what we said before. When P is trivial. And last, when the dimension of sigma is equal to 3. And this is basically the theorem before. Okay, thanks a lot for the attention.